Hello and welcome. This is going to be our lecture video for the second quarter final test review in ChemCom. Let's go ahead and get started with number 1. So we're given 5 elements. Let's write their symbols real quick so that we can use those symbols in answering the questions. We have nitrogen, oxygen, neon, silicon, and phosphorus. So before I start putting these in order, I'm going to draw a little periodic table. I'm just going to zoom in on the upper right where these elements are and just going to put them in their relative spots. So we've got neon right here. We've got nitrogen and oxygen. We also have silicon and phosphorus right below like this. So silicon, phosphorus, nitrogen, oxygen, neon. So put the elements in order of number of protons. Well, that's just the atomic number. We can just put them in order of atomic number, and it turns out they're already in that order. So N, O, N, E, S, I, and P. That's how the periodic table is organized, principally by atomic number, and then the reason they're in the rows they are to match up valence electrons, or I should say columns. So put the elements in order of atomic radius. So here we've got to remember a trend. It makes sense that the atomic radius would get bigger as we go down the periodic table, but the less intuitive one is that it also gets bigger going to the left. And the reason for this is that when you are within a period, you have the same number of energy levels, but you're getting a stronger and stronger nucleus because you're adding more protons. That stronger and stronger nucleus is able to pull in on that energy shell with greater force, and it shrinks in the atom until you have to add a new energy level. So all the new electrons are just going into that same energy level, but they're being pulled in harder and harder. So for this one, we kind of reverse it, but neon is going to be the smallest. It's only got 2 energy levels, and they're being pulled in very strongly with 10 protons. Then oxygen, then nitrogen, then phosphorus, then silicon. All right, so ionization energy. This is how hard it is to remove an electron, and it's the exact opposite of atomic radius, because electrons that are closer into their nucleus are going to be being pulled in much harder by that nucleus, and therefore much harder to remove. And noble gases are very hard to remove. So this order is silicon, phosphorus, nitrogen, oxygen, neon. We just completely reverse this one. And now for electronegativity. Electronegativity is a little bit different, but with electronegativity, it follows the same trend, but noble gases have very low electronegativity. Electronegativity is a kind of different way of looking at the electrons. It's not necessarily how hard it is to remove an electron, it's how much the atom wants to add more electrons. And so as we go up and to the right, we've got a strong nucleus whose positive charge is unshielded, and we're also getting very close to an octet. And so elements, especially in group 17, really want to gain 1 more electron so they can reach an octet. So it's going to be very similar to ionization energy, but we're going to move neon to the front because neon has very little electronegativity. It's already got 8 electrons in its valence shell. It's good. It's just chilling. So we'll just move it to the front, and then it's the same order. So we got all of these orders based off of the trends, which is what I would expect you to do in the test. The last thing we would want to do is double check using an actual chart of values. And it turns out there's actually 2 that need to be reversed here. Surprisingly, nitrogen has a slightly higher ionization energy than oxygen. And that just shows us that these trends are really useful tools, but they're not perfect. There's other things that can affect things like ionization energy or electronegativity other than just number of protons, number of valence electrons. There's other things to consider when we're talking about the stability of an electron. So here, these should technically be swapped. On a test, I would accept either order if you knew something about some of the exceptions to the rules. I'm just expecting you to apply the trends. All right, let's move on. Draw a periodic table below and draw an arrow for the trends. So we should be getting good at just drawing the outline of a periodic table by now. Kind of looks like that. All right, and then you can draw them as diagonal or on the outsides. Sometimes I like on the outsides because then it shows the kind of two separate trends for groups and period. So atomic radius is going to increase this way and this way. So we'll have red be atomic radius. All right, ionization energy will increase this way and this way. So blue will be ionization energy. And then electronegativity will increase in the same direction, with that exception that the noble gases are kind of blacked out. They have very low electronegativity. So then that's green will be electronegativity. And then we can just say 0 electronegativity here. And now there are exceptions to that as well. It's with, I believe, krypton and xenon. They have measurable electronegativity, and there's some kind of strange explanations for why. But as a rule, and because we normally just deal with the top of the periodic table anyway, noble gases have no electronegativity. All right, next up, let's name and draw a Lewis structure for the following ionic compounds. We're given a hint that these are ionic because the problem says ionic, but we could also figure out that they're ionic because they include elements in periods 1 or 2, like calcium or magnesium down here. And then with tin chloride, we'd have to look at the electronegativities to see that those are pretty far apart. This one might actually end up being covalent, but we'll just treat it like it's ionic for this problem. All right, so the names would just be calcium bromide, tin, and now tin, this one, it's low enough on the periodic table that it needs a Roman numeral. So it's going to be tin 4 chloride. Chlorine can absorb 1 electron each, so we need tin to have 4 valence electrons. Yeah, once you get low enough, or when you're in the transition metals, you need to be including that Roman numeral. And then this last one will be magnesium. And then that PO4, we need to know that that is a phosphate group. And phosphate groups can gain 3 electrons. That's why we had to do a 2-3 ratio here, because magnesium can lose 2 electrons, so this makes it an equal transfer of 6 electrons. All right, now back to the Lewis structures. So with calcium bromide, we've got the calcium has lost its valence electrons, so it's got a 2+ charge. And the bromine has gained them all, so it's up to 8 electrons. And each bromine gained 1 to give it a -1 charge. And then there's 2 of them, so you can put the 2 here. Sometimes I see the 2 in front as well. All right, next up is our tin 4 chloride. So the tin, SN, has lost all 4 of its electrons, so it's got to have a 4+ charge. And then the chlorines each gained 1, so there'll have to be 4 of them, all with a -1 charge. And then we'll keep everything equitable there. All right, and now for our big one, the magnesium 3-phosphate. Well, don't say magnesium 3-phosphate. It's really magnesium 2 because it's got 2 valence electrons. Well, if you're going to say the 3, you have to say Mg3PO42. All right, so this one, we've got our magnesium. That was an N. That's lost both of its electrons and taken on a 2+ charge, and there's 3 of them. Then we have our phosphate. So this is a Lewis dot diagram. So we'll start with the phosphorus in the middle. It's got 5 valence electrons, which it rearranges in a way to bond to 4 oxygens. I don't believe it keeps an ordered pair. We'd have to really draw this out to figure out if it does. But I'm pretty sure it just looks like this. All right, and it gained 3 electrons. That makes sense that it would have lost that lone pair because each oxygen takes 1 electron and then the lone pair goes out to one of these oxygens. And then we've got, so that's got a 3- charge, and we have 2 of those. Okay, I just looked it up, and actually the phosphate, when it sends its 2 electrons over to one of those oxygens, it actually makes a double bond. So I've got to erase, a tiny little eraser, and then form a double bond. Is that the absolute most accurate way to do it? And then all the electrons actually do balance out. The one on the test, I will not take off points if the actual ion here is messed up. It's more about getting the charges and the numbers at the bottom correct. If I have you do a polyatomic ion for one of these. All right, write the chemical formula for the following ionic compounds. So for these, we need to know how many electrons are going to be transferred. Sodium's in group 1, so it's going to lose 1. So right below it, we should write lose 1. Bromine is in group 17, so it wants to gain 1, so we can get to that perfect octet. So that's just a perfect 1-to-1 relationship, so it's just going to be 1 sodium, 1 bromine, and we're done. Aluminum wants to lose 3. It's in group 13, so it's got 3 valence electrons. It'd like to lose them all. A nitrate group can gain 1. 1 electron total for the whole group. And so we have to do a 3-to-1 ratio to make this work. So it becomes Al, and then nitrate is an NO3 group. And then it gets parentheses, and we get 3 of those. Notice we swap the numbers. The 3 comes over to the nitrate, the 1 comes over to the aluminum to make that work. All right, and then there's chromium 3 sulfide. That 3 tells you that this chromium has 3 electrons, so it's going to lose 3. And then sulfide group. So that's not actually a group. That's just a sulfur because it ends in "ide." And we see that sulfur wants to gain 2. So we're going to do a 3-to-2 ratio. 3 on the sulfur side. And I could use a color change here. Let's go. Chromium is Cr. It gets a 2, and then sulfur is just an S, and it gets a 3. All right. Name and draw Lewis structure for the following covalent compounds, and as well as identify their molecular shape. So Cl2. This we would just call chlorine. Also fine would be dichlorine. When it's just a single atom like this, it's okay to just call it chlorine. And we would understand that it has to be a Cl2 so that they can share 1 electron and both get up to an octet. And this is what that looks like. We've got the Cl bonded to a Cl, and they both have got 6 more electrons around. The bond counts as 2, and that's why they're able to both say that they have 8 electrons. All right, this shape, it's only a single bond with 3 lone pairs on either of these. So that is definitely linear. Every single bond is always a straight line. You have to get multiple bonds to create more complex shapes. All right, HF, we would call this hydrogen fluoride. Remembering to end in "ide" there. And our hydrogen has got that 1 valence electron, which will just bond up with fluorine's 1 valence electron. And again, just a single bond. This is linear. Next up, H2O. So to name this, it's got to be dihydrogen monoxide. Or monoxide. Also, I'm realizing I messed up here. Hydrogen fluoride should be hydrogen monofluoride. The second word always gets a prefix with covalent bonds. So even I can mess up, but at least I go up and fix my mistakes. I'm still thinking a little bit ionic when I wrote hydrogen fluoride instead of hydrogen monofluoride. All right, dihydrogen monoxide. So we've got the 2 hydrogens with their 1 valence electron, the oxygen with its 6, which it puts into its orbitals 1, 1, 2, and 2. And then that unpaired comes over and matches up. The orbitals overlap. And now we've got 2 lone pairs, 2 bonds. Well, that's always going to be bent. The way we can think about it is that these lone pairs push on these bonds to bend them out of shape. All right, now we all know this one. This is carbon dioxide. Carbon dioxide. That carbon is double bonded to 2 oxygens and has no more lone pairs on it. So that's very important. Without the lone pairs on the carbon, this stays linear. All right. Now, nitrogen trihydride is a nitrogen, which has 5 valence electrons, so 2 of them get partnered up, and then those unpaired ones all bond to a hydrogen. All right, so we have 3 bonds, so this shape should definitely start with tri, and then we have to decide if this is trigonal planar or trigonal pyramid, and it's all about this lone pair on nitrogen. That lone pair pushes this into a pyramid, so this is trigonal pyramid. Or trigonal pyramidal is fine as well. All right, CH2O. Although it's got that H2O in it, it looks very different than a water molecule. Always put carbon in the middle. The name for this is formaldehyde. You do not have to memorize this one. But that is its name. We could try and say something like carbon dihydride monoxide would be fine, but the name is formaldehyde. And so we put carbon in the middle. It can make 4 bonds. But what happens is that 2 of these bonds go to an oxygen because oxygen's got the 2 unpaired. And really what I do is I bond to everything and then look for the double bonds, and then I see that I can make a double bond to oxygen. But I've drawn formaldehyde so many times now for you guys that this should just look familiar. We know that this is trigonal. The double bond just counts as 1 bond, and we've got 1, 2, 3 bonds. So it's trigonal, but there's no lone pair, so it ends up being trigonal planar. No lone pair to push this triangle into a pyramid. All right, next up we have carbon tetra. Tetra is 4 hydride. All right, so you got carbon in the middle. It's got its 4 lone pairs. They all just go to 1 hydrogen, no room for any double bonds. We've got 4 bonds, and whenever we have 4 bonds, the shape is always tetrahedral. tetrahedral. All right, some more naming covalent compounds. I'll just do this one out loud to make it go a little bit faster. We have hydrogen monochloride, carbon dioxide, nitrogen trihydride, dinitrogen tetraoxide, diboron pentahydride, sulfur hexafluoride, phosphorus heptabromide, tricarbon hexahydride, tetraphosphorus nonasulfide, and heptascandium decachloride. All right, so we used every single prefix we've learned in those. So hopefully that was some good practice. So now use the following chart to help determine if the following compounds contain polar or nonpolar bonds. So oxygen and hydrogen. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. That gives us a difference. So if I just subtract these, that gives us a difference of 1.4. Well, 1.4 is in the range between 0.4 and 1.9, where we say a covalent bond is polar. All right, phosphorus and sulfur, we've got 2.2 and 2.5. I subtract them, I would get negative 0.3, but we'll just always do the absolute value of that, so 0.3. That's in the range of 0 to 0.4 that we call nonpolar. And then carbon and carbon, I don't even have to write these down because anything bonded to itself is going to share its electrons equally and be nonpolar. All right, in a covalent bond between tin, right there, and nitrogen, right there, around which atom will the electrons spend most of their time? It'll be the atom with the higher electronegativity, so nitrogen. What are the consequences of this? We can say nitrogen will be slightly negative. We could also say we create a dipole. So this bond will kind of act like a magnet with the nitrogen end being negative and the tin end being positive. At the end, you've got some vocab to memorize. You will see this again on the test, so memorize it. Pretty please. All right, that's that for this lecture video. Have a good rest of your day.